I think we can get started so that we could just get started on studying for finals early, because I know every one of you would love to do that. But first off, welcome. Thank you for everyone that is coming to the very first Solicar fall semester recap, braving the cold and being here. We're really excited for everything that we've working on this semester and what we're doing next semester. But if you didn't know, my name is Josh.
My name is Kevin.
And I'm the president of Solicar, and Kevin's the engineering director. So we run the things here, and there's a bunch of other lovely people here today, but we'll go cover them later. So, coming up, first, we're going to go over the challenges that we've faced over the semester and how we've been improving ourselves. Then we're going to go see what each team has been doing. 1, operations, 2, electrical, and then mechanical. And lastly, we're going to go over our timeline and schedule for the spring semester. And stick around till the end for some light refreshments, ask questions, and give feedback potentially. So, some of you may be wondering, what is Solicar? So obviously, we build a car and race it. And as an experimental learning program, we give undergraduates the experience outside the classroom. However, to me, it's more than the end product of finishing the car. It's about the process behind it. It's about the skills you build from collaborating, learning, and innovating. It's about the skills that can take you so far, and that's the mission of Solicar. So develop individuals for the real world and what comes after college. And after Solicar, you can work anywhere from some of our alumni is Ford, NASA, SpaceX, GE, Microsoft, Rolls-Royce, and many more. Additionally, we are also a community. We're also 100 members strong, interdisciplinary, and coming from several schools across UVA. We support each other outside academics, and we make memories together. And we provide a unique experience to our members. This unique experience, in fact, is working on Rivanna 3. So this is Rivanna 3. It's the 3rd ever iteration and named after the Rivanna River. Rivanna 3 was a bold step forward. It was the next step for the team, in which we embarked on a multi-year process to design and manufacture it. However, Rivanna 3 has been riddled with a bunch of challenges. There's been multiple design changes, financial difficulties, and poor timeline planning. And evidently, these problems arose during our competition, and we couldn't compete in our competition, unfortunately. However, while this set us back, this doesn't stop us at all from improving and rising again. Because this bold step forward was not meant to be easy. It must be faced with everything we have. And with this, we come to now, the Solicar fall semester recap. So, you may be wondering, why are we doing this? 1, for the sake of transparency. Solicar has had not that much outside connection to the engineering school, has been practically closed off. However, we need to establish a proper pipeline connection so we can potentially increase support of the team. 2, we need to get used to the goals we set. The fall semester recap is a good intermediary goal to get Rivanna 3 completed on time. We can apply the lessons we've learned from planning and executing this presentation to support our efforts in meeting deadlines such as design processes, more presentations, and our future goals that we end up making. 3, we want to get in a better mindset into presenting our work to other people, especially for design review purposes and developing skills in general. And 4, we want to prove that we are on track to be competition ready. We want to show that we mean business, that we have what it takes, and we are able to get Rivanna 3 into a great and efficient car. So next, I just want to go over the state of the team. I just want to go over some of the challenges that we faced throughout the semester and some things that we have or plan to do next semester to overcome some of these challenges and mitigate them. The first challenge is that we were unable to compete at the competition. It was basically a rush car. As I mentioned before, Rivanna 3 was poorly planned, where we missed deadlines, wasted time, and wasted money. And this led us not to be able to race that competition. Now this year, we want to change how we think about how we go about solving this new problem that we have, how to fix Rivanna 3 to be competition ready, and it starts with the team structure itself. To start, with a new exec, these lovely people are very talented and committed to their work. We've set and defined their responsibilities so they understand the role and they can be effective within their members and their sub-teams. Additionally, we have committed higher leadership that are actively supporting the team and their leads. Additionally, we do have an emphasis on supporting each other. If one of us needs help, we'll help them. The second one is that we need to understand what we're able to do. There's around 12 weeks in the semester with limited time to do everything. Rivanna 3 can't be manufactured in a single year, no matter how hard we believe that. And we understand that all of us are students and academics are first. And so a car is something that we all do for the love of our hearts. This year, we are only focused on Rivanna 3. Under these circumstances, Rivanna 3 will be pushed off to a later time. We must make Rivanna 3 the best before moving on. Third, better external support. As I mentioned before, transparency is key. The more eyes on our project and the more eyes on Rivanna 3, the more feedback we're able to have and the less mistakes we're able to get. Because mistakes cost time and money, which we both don't have. This semester, we've moved to a wonderful new advisor, Professor Barnes, who really supports us and believes in what we do. We have a new ELF director, Professor Garner, in which he really supports us and he really pushes us to doing good. This semester, we have a huge emphasis on design reviews. We want experienced people helping us on designs because it's key for having a high-quality product. Each design that we will go over today, which each sub-team lead will present to you, underwent at least 3 different phases of the design review. Last one is enhanced documentation. We want to emphasize on the processes that we're going through, and we want to document every single lesson, principle, in every single step we do. Additionally, this is really good for future cars for when we have Rivanna 4, 5, or 17. Next semester, I'm proud to introduce that we're using Google Workspace through a nonprofit. Everyone on the team will get customized Google accounts to collaborate effectively and properly to document the work. Additionally, this serves as cloud storage for centralized purposes, and this is way safer than what we have been using previously. Next is the relocation of our workspace. Over the summer, we got relocated to a different floor at our space that we operate, which is in the picture on the right. This was done over the summer, so the lack of people that has been working on the car, we strained ourselves, and that pushed Rivanna 3 back even further. Additionally, this overall was almost 40% reduction in space, and it's been pretty challenging to fit all of our members and operate properly. However, with this, there are some plus sides. One, we're able to start fresh, and we were able to start over. We're able to properly organize all of our equipment and materials in a more efficient way, and we're no longer sharing a space in order to misplace items. This semester, we're slowly organizing and making space hours, and we wanted to make the space more appealing to members, more inviting, and add more decorations. And we're really excited on how this place can serve us in the future. Lastly, we were hit hard with the unfortunate news that we're getting less funding from internal UVA funds and grants that we get every year, which is around a fifth of the amount we usually get. While we are still financially stable with the amount of money in our accounts, budget is still something to worry about. In order to mitigate this and to make sure that we're able to safely compete, complete our projects, and go to competition, we want to make sure that we never go over budget. We have a proper management system to make sure that we have smart saving, stretch our budget as much as possible, and this starts how we manage our budget and how we properly document it. Starting next semester, hopefully we introduce a treasurer. Over the years, either the president or another director, such as the operations director, did the budgeting, which, as far as I know, is not a good idea. We need to spread out the workload amongst our leadership, and a dedicated person working on purchases will lead to less mistakes. Lastly, we're moving away from internal funding sources. From the Experimental Learning Fund and Parents Program, we want to be more independent and less reliant on this due to the circumstances we face. We will be expanding to more donation-based and sponsorship-focused models, and Thea, our operations director, will explain it more when he presents.
So now, getting into our goals for this semester and this year as a whole. First is obviously we want to race in Formula Sun Grand Prix, which is a competition that we've been racing in for the past 5 years. In order to qualify for this competition, you have to send in some detailed design reports that are then reviewed and approved by the race regulators. Then once that gets approved, you go down to the race, which this year is most likely going to be again in Bowling Green, Kentucky. First, when you get to the race, there are 3 days of what they call scrutineering, which is a rigorous technical inspection, where they essentially look at your car's mechanical systems, electrical systems, to make sure that it's safe and ready to race on the track. Then, following that, if you pass scrutineering, you do 3 days of track circuit racing where you go in a circle, and whichever team completes the most laps wins the race. So this is obviously our goal that we want to go for this year, but there is a level of competition above Formula Sun Grand Prix, and that is the American Solar Challenge. And in order to reach this level of competition, you have to qualify by completing 200 miles in 1 day or 300 miles across 2 consecutive days in the Formula Sun Grand Prix. With the American Solar Challenge, if you do qualify for that, it's a cross-country race. It takes place over the course of a week. It's usually on a historic trail. That being said, as a team, we don't necessarily have the funding and logistics ready to participate in that competition, but it is certainly our goal to hit that qualifying mark in the Formula Sun Grand Prix, which is something that has never been done before in the history of our team. So we're very excited to push for that goal and kind of get that first tick off for our team in terms of a milestone and accomplishment. How we're going to get there? In looking at Formula Sun Grand Prix's 2025 results, we notice 2 main things about the top teams and the top placers, and you can see the results here. First thing we noticed was a quality of reliability in the cars that placed at the top. And what I mean by that is when you look at the lap count for across the 3 days, you see a pretty consistent level across the top level ones compared to the bottom level ones. And what that means is that their cars are robust enough and easy for maintenance, so that if there is an issue, they're able to take into the garage and get back on the track as fast as possible. So when you look at the designs in the upcoming presentations, we really wanted to emphasize the point of, 1, robustness, to make sure that these systems that we're building are able to race across 24 hours across those 3 days. But 2, also a level of maintenance, so that if something does go wrong, we're ready to respond as fast as possible. And you'll see that with our battery, which is now more easy to remove, or our top shell hinging, which allows us to access the mechanical components of our car more easily. Then the second thing we noticed was a quality of readiness. And you can see that the teams that were placed at the top were ready to go on the track from the jump, and they were able to just start getting the laps as fast as possible. So that is something that we are planning for this year by having our car built more sooner into the spring deadline or the spring semester, so that we have time to test our car for the reliability, so that hopefully once we get to the race, we can get to scrutineering, breeze through it, and then hopefully get on the track ready to go and start cranking out those laps at the qualifying mark. Now, to get into the actual meat of the presentation, just to introduce our executive structure before they come up and present. Again, that is Josh. He's the president. I am Kevin. I'm the engineering director. You can kind of think of me as the vice president. Then the actual powerhouse of the team is everyone else. So we're split into 3 different branches. We have mechanical, electrical, and operations. And within those, we have directors at the top. And then underneath are the different sub-teams with leads at each. So we have aerobody composites, chassis, brake and steering, suspension, power, solar, hardware integration, telemetry, embedded, and then finally marketing and sponsorship. So with that being said, we'll first get into our results as an operations team this semester. So Theo.
Hello everyone, thank you guys so much for coming out. We're the operations team. My name's Theo, I'm the operations director.
My name is Alina and I'm the marketing lead.
Unfortunately, Rodwan, he's the sponsorship lead. He couldn't make it today, so I'll be covering some of his slides. So getting started here, as the operations team, we're really doing everything that's not engineering related on the team. So this semester we set ourselves a few goals. Mainly we want to diversify our revenue streams, as Josh was mentioning. This is really important for us to kind of stay independent as a team. We've been doing this for things like concessions at UVA sporting games, as well as CIO challenge and donations from our own sources. Doing so, we also want to encourage a strong team culture across our teams. Obviously, everyone's kind of coming from their own major backgrounds, so we really want to encourage that kind of synergy throughout the teams. And finally, we want to kind of modernize the web presence. A lot of it was using old websites on things like Google Sites and stuff. So getting that up to date and getting ourselves more presence online was really important to us. Doing so, we tried to improve a few aspects of the club, meaning the organization, the interactions that go sub-team to sub-team, clearing up our financials as Josh has been talking about, and for our sponsors, getting ourselves a stronger program to be able to reach out and obtain these sponsorships. Doing so, Alina also made a lot of marketing content for us on all of our pages. It was really good at kind of pulling in the sponsors and getting more authenticity for our team. Now to get more into the finances, we are now a lot less reliant on UVA funding sources, as unfortunately this has dropped. If you can see our breakdown of funding, ELF Parents Program make around 30% of the total, where now our other financial sources are coming in to kind of supplement this. Our biggest ones have been from concessions, as we talked about, and also the donation of our alumni and our club members to things like the CEO Challenge. So it's been really great to work with. Looking ahead, we want to get more applications into grants. We have a pretty good list of them that opened in the spring semester from last year. So we're going to go back through those and try to expand that even more. As well, get involved with every fundraiser that UVA offers. And finally, just want to connect more with the alumni. It's a great network, so it's really important to maintain that. Now for sponsorship, this is the team that's actually doing the reaching out to these companies and managing these relationships, seeing what we can get out of that. So the team has been up to a bunch, including sending tons of emails out to companies, doing a lot of their own research on brands that would be great fits with us. And this has brought us a lot of cans of Monster for one. So we're going to be continuing this up and making sure that the team stays energetic. We've been revising our sponsor pack, which is a list of like kind of what our team offers, what our structure is for donations and stuff like that. So making sure that was up to date was important, as this is included in a lot of our outreach materials. Finally, we're including our alumni network a lot more. We're able to talk to some of the connections there. And it's been a good tool to kind of find out where we want to navigate through these sponsorships. Continuing with things like we've been talking about with the challenges and the concessions has been really important. And there's so many more opportunities in the spring, including things like video challenges and stuff that we'll be up to try and get more corporate sponsors.
Up next is the marketing team, and my sub-team, we've been focusing on creating newsletters to mass send, social media posts, promotions, the social events that you guys attend, and Charlottesville outreach. And so this fall semester, we've focused specifically on sending bi-weekly emails, and this consists of recipients such as you, your parents, your family, friends, sponsors, and with that also comes with constant Instagram posts. We've reached over a 40% increase in the amount of new accounts that we've exposed. And as of right now, we're trying to expand our social media outreach into TikTok. So if you guys see us creating some new material, come say hi. We've also participated in Charlottesville high school events and other SEAS events, as you'll see in some of the pictures. And team bonding wise, I think we've managed about 2 events each month. You all have probably attended one or two of them, such as the hike to, where is this again? Humpback. We've had the opportunity to do trick-or-treating on the lawn. We've also met Stanford Solar Car's president, as well as a mixer with Mars, where we had the opportunity to learn a lot from their team and their experiences. And next up is electrical team.
All right, everyone. My name is Will. I'm the electrical director.
I'm Liz. I'm the power lead.
I'm Aaron, I'm the solar lead.
I'm Colby, I am the embedded lead.
I'm Ethan, I'm the telemetry lead.
And I'm Troy, I'm the hardware integration lead.
So before we get into what these guys have been working on all semester, I want to cover some high-level goals that we've had for the semester and the year as a whole. As Kevin was mentioning earlier, one of our biggest goals as a team is to improve reliability. We want to get on the track as soon as possible and then stay on the track the entire time. We want to minimize things that can go wrong, and when things go wrong, we want to be able to fix those as fast as possible. Some of the issues that have hurt this team's race performance in the past on the electrical side have been some basic wiring issues. Little wires would come out, or they would break, causing us to have to take the car apart to figure out what went wrong. 2 summers ago, we had an issue with bypass diodes, which basically they improve the efficiency of our solar panels, but we did not have those, which killed the power that we were getting from the sun. We've had a lack of analytics from the car. We've had a lack of information getting from the car to people outside so we can do some analysis. We had 2 times over the last 2 years we had our microcontroller break. These were smaller issues, but they happened at very unfortunate times. Set the team back, taking away valuable time to work on other things. And we also are going to be improving our battery pack reliability with the new pack. So some of our ways that we're going to be trying to improve this are just making the car more robust, minimizing points of failure. We're doing that both through some careful design and some extensive testing. The power and solar teams are working to increase the efficiency of the car a bit. And our software teams are working hard to gather more system information, getting information off the car and to people outside so we can do more analysis, optimization, and debugging. I'm also going to give a little rundown of how our car actually works. So I'm going to separate this into the low voltage system and high voltage system. The low voltage system operates at 12 volts. When you first turn the car on, it actually runs off a separate, smaller battery that can let the car make sure everything's okay before turning on our higher voltage battery pack. So this low voltage system has a handful of PCBs, most of which we make ourselves custom. Some of them have microcontrollers. We have our 2 current microcontroller boards here. This top one handles all of the logic operations for the car, and this bottom one is for telemetry data to gather and transmit them. We have other PCBs as well that are smaller, cheap ones that are just to handle wiring distribution, make things a little cleaner and more reliable. We have this steering wheel for our car. It has a screen in it that also has a microcontroller on it. That handles all the driver interface, the buttons they have to press, and it also displays dash information to the driver. All these systems talk to each other on a protocol called CAN. It's a set of wires that strings throughout the car and it gives the same information to every piece on the car. This low voltage system just handles everything from switching your turn signals to telling the motor how fast to drive. So our high voltage system starts with the battery pack here. This is our previous year's battery pack. We're making a new and improved one now. But this is going to operate at 132 volts. It plugs into a motor that we purchased from a company called Mitsuba. It comes with its own motor controller. We also have a BMS or battery management system. This is something that we purchased. It checks over the battery pack during operation, make sure everything is safe. It'll give us information on what's going on and also be able to check if things are going wrong and shut everything down. We have our solar panels on top of the car that plug into these boards over there. Those are called MPPTs. They convert the power from the solar panels into something that can actually charge the batteries. That's another thing that we buy ourselves.
Okay, yeah. So I'm Ethan. I'm the telemetry lead. So what is telemetry? Telemetry is basically just most of the off-car software that focuses kind of on the getting the data on the car from the car to us, so we can actually see what's happening with the car. So yeah, we've been very busy this semester. This is kind of the second full year of having a real telemetry team. So we've been working on a lot of new systems for the car. So first is a new data transmission pipeline using LTE, so like the LTE phone plan that your phone might have, for example. Using getting a new race dashboard to be able to like display all of that data and visualize it for like the pit crew during the race, as well as a new simulator for the race, and then just kind of whenever to be able to analyze like and simulate the car's performance during a race, given like cloud coverage and solar irradiance and all those sorts of things. And then last, we also reworked the driver screen that Will mentioned to just be clearer for both debugging and actually during the race as well. So yeah, starting with the driver screen. So you can see on the left there is kind of the old screen. I made that so I can say it doesn't look amazing. It's kind of all over the place. So we wanted to kind of split up the screen, make it easier to kind of understand. So now, and also leverage like the touch screen capabilities of the screen. So kind of what we realized is there's two main things that people use this screen for. They use it for the actual race, and then they use it to like debug stuff on the car just whenever. So we kind of wanted to make both of those things easier to make happen, essentially. So we kind of divided it into two screens depending on what you want to use the like car for at any given time, essentially. And then we also, it's easier to add new screens or change things in the future, depending on how the data on the car might change. Yeah, and then the next project is LTE. So the current system we have is like RF point-to-point radio, so from one radio to the other. And this is kind of like another secondary system that we can have. This one might be better at range, for example. So during ASC, when we're not always right in front of the car, we're able to still send messages. So kind of using both of these systems, we're able to get more reliable data transmission from the car to the pit. And then this is kind of like a oversimplified diagram of essentially the architecture for this project. So we have our like XB LTE module that sits directly on the car and is attached to the car, and then that goes to AWS. And then from AWS, it goes to both a database, so we can like do whatever kind of data analyses we want with it at a later time, and then also just is displayed in real time on the race dashboard for the pit crew during the race. And yeah, next project. So the race dashboard. This is kind of like the end product, I guess, of a lot of these other projects. For example, like with the data transmission and with the simulator. This is what's going to display everything to the pit crew and just to whoever is looking at it. So we built this using React. That's a framework for these like web apps like this. What's nice about it is it's very modular, so we're able to change things in this very quickly depending on how the data needs of the car change. So this is just kind of a work in progress of what the screen might look like using just kind of mock data. So it'll display all of like the important information, the most important information at the top, and then kind of just anything that the pit crew might need to know about the car when we're actually performing during the race. And this will have like all of the data streaming from the XB LTE, from the RF modules. I might also have the display for the simulator that I'll get to in just a second. But yeah, it'll kind of just show everything that the pit crew might need to know about the car. And then the last project is the battery simulator. So basically just like a Python-based project to model the energy performance of the car and kind of predict how much energy we will have, like, maybe an hour or 2 hours in the future. So we can like actually have a race strategy and make decisions about if we want to keep doing laps or if we need to recharge and that sort of thing. So it pulls live weather data from a API, and we can use that and all of these different parameters that we can tweak to be able to just make predictions about how much battery we think the car will have, in the future, essentially. So we can use this during the race in real time, like using the actual data we're getting from the car, and then we can kind of predict what we want to do during the race. But we can also just have this as kind of a static tool that we use at any point during the year, given like different assumptions about maybe how heavy the car will be or how aerodynamic it'll be, and then we can use that, even far before the race to be able to figure out like what we want to optimize for when we're actually building the car. But yeah, I think that was everything.
Hi everyone, I am Colby. I am the lead of Embedded. So our main goal is to make the software that goes on the vehicle and controls the car itself. So what have we been up to this year? So one key project has been transitioning away from EmbedOS, that was our real-time operating system, into a new custom solution. We are also adding many new features, and finally we are updating our existing code to adapt to hardware changes. So first on the new features. So every feature has a big reason why. So on the first one, so we want to be able to detect which kill switch has disabled the car. So at the race, there was multiple times this past year where just the car would not turn on and no one knew why. And then half an hour later, we found, say some kill switch on the back was engaged and no one checked that. Or maybe even it was unplugged. So we want to make that process of debugging much faster and just log immediately, this kill switch was engaged, this one was unplugged, that's why the car will not turn on. Secondly, many of our PCBs can be in hard to reach places, and to upload code to them, you must plug into them directly right now. Well, as the car has a radio now, why not just upload that code over the radio? We are planning on doing that this year, and that will allow us to then get code onto the car much faster with more ease. Next, we are working on a new ignition system. So right now, if you want to turn on the car, you first turn on a switch for LV, then wait a few seconds, wait to hear a few clicks in the battery box. You then enable HV, then wait a few more seconds, and then turn on natural motor. This system does the job, but it is just not a great system. And if you turn stuff on too fast, then you could potentially fry some components. In fact, that's how we think we fry the microcontrollers over the past few years, by turning on HV too fast. So instead, we will have the system be checked by software. That way, if, say, you've not waited, say, 3 seconds, then we can say we'll slow down and then don't actually engage HV until the time has passed. So we can have a safe ignition sequence. Also, we will log data to an SD card on the vehicle. So right now, while the vehicle is producing log data constantly, if you're not plugged into it, that log data goes nowhere, and then if something went wrong, you would never know. But instead, we'll log all the data to an SD card. That way, if, say, there was some big incident on the track, we can then just read the SD card and see what went wrong and how to avoid it in the future. We are also leaving EmbedOS and going to our own custom solution. So what is EmbedOS? Well, that was a large real-time operating system that was common in embedded systems over the past decade or so. That being said, it has reached end of life, and the people who develop it have said even to not use it any longer because they will no longer support it. So eventually the team has to make a new solution or find a different one, and we chose to do this year. Also, just the system, it doesn't even work on all the hardware that we use. Like, it does not work on the screen that goes in the steering wheel. So we have decided that this is the time to make our own custom solution to replace this. And the name of that is Photonic OS. This is our own custom real-time embedded operating system that we are using this year. So how is it made? Well, thankfully, there was many other libraries online that we could use to help make this system. Making a whole operating system is a huge task, and thankfully we can use those resources. So the kernel of the OS is the FreeRTOS kernel. So all that means is that's a system that provides multi-threading and other support for concurrency. Now, what does that mean? Well, say you want to do multiple things at once. Say that you want one function to read your CAN messages, one to control the motor, and one to flash the tone signals. All those things need to happen at once, and the best and most safe way to do that is to use multi-threading, and that is provided by a real-time operating system. Also, we're using the drivers that are provided by STM. STM is a company that makes the microcontrollers themselves. So we're using their low-level drivers and then wrapping them in our own high-level C++ drivers. This enables us to have just a much nicer interface as well as provide new functionality to those drivers. We're also adding a ton of our own library code as well to add in new features to the system. And then finally, we're using the fat file system, which is common in embedded systems, to control the SD card and allow us to have files on that SD card. Thank you.
Okay, so power and solar up next. So what Power Team does is we're in charge of designing, fabricating, and creating basically the battery system and everything that goes into that. And the solar sub team, if you want to say.
We're in charge of making sure that the solar panels are made, manufactured, and implemented into the car.
So what have Power been working on this semester? We've been disassembling the old battery pack. We've been designing a new battery pack, a new battery housing, as well as custom parallel fusing current collectors for the battery pack. And overall, we've also been teaching new members how to CAD, design PCBs, spot weld, solder, design battery packs, and much more. So why are we creating new battery pack? Well, as some of you may know from the old pack, it was very confusing to assemble, required multiple tools to assemble, it was very time consuming, and it was really easy to bridge modules, which created a safety hazard. And additionally, the battery enclosure and securement it was really hard to fit the pack into the box. The distribution system was in an external container. We needed a crane to actually get the battery pack and enclosure into the car, and even then it was hard to align the L brackets in the chassis to make it fit in. And we also required a ratchet strap to secure the enclosure into the chassis. So with this, we have the new battery pack, which we all named Big Buzz after a vote. The specs of it are 32 series, 10 parallel with a nominal voltage of 115, a maximum of 134, with a capacity of 5.18 kilowatt hours. So for the overview, as you can see, it's 4 separable sections, each with 8 modules, and we have a staggered cell design, so we have a more condensed pack while still allowing airflow through the pack. At the top, we will be having a PCB to hold all of our voltage taps, fuses, and you can also see the orange little squares at the top. Those are our rad-lock connectors, so they are fast, tool-free, and very secure connections between the sections. We also have a polka yoke design with the handles so that you cannot incorrectly wire up the pack, such as putting positive to positive and negative to negative. And then, as you can see over here, we have current collectors that we created ourselves with parallel fusing to protect the battery pack modules. We also designed the enclosure for our battery pack. So, different from years before, we will be housing the pack and distribution side by side, not just in a different container or on top of each other. And we're going to be using a new material, which is going to be 6061 welded aluminum, which is more durable, lightweight, and require less fasteners to hold together. And to make the inside non-conductive, we'll have a thin Garolite lining, and the electrical ports will be attached to the sidewall of the housing enclosure, so that it's easy, fast, and organized to make connections to the motor and solar systems. For securing the pack and the enclosure into the car, we have an X-shaped skeleton over there to secure the pack. Easily slide the pack and secure it into the enclosure, and then there's U-rails on the enclosure itself to slide it into the chassis, and we'll use clevis pins to hold it in place.
Hello, I'm Aaron again, and I just want to give an overview of what Solar's been doing this semester. So the main thing we've been working on has been onboarding. Unfortunately, I'm the only returning member of the solar sub-team from the last year, so a lot of this semester has been focused on skills training, and what you see in the top left photo is me teaching our members how to solder and wire panels together, which is a core skill of the solar sub-team. We've also been working on this semester on planning for the array expansion. Our current array is 4 meters squared. We'll talk about this a little more in a minute. We're going to expand it to 6 meters squared. Also, a big thing we've been doing this semester has been assisting power, and that's why we've combined solar and power this season because of the need for the new battery pack for just more members to help out. And we're also planning new attachment methods for the panels to the car. As you can see in this further right, the panel's been curving up a little bit, even though they're glued down. And so we're going to be working on new ways. We've been working on new ways to make sure the panels stay flat and flush to the car. Okay, just to give an overview of our array, our current array on the car right now is 4 meters squared per previous race regulations. It consists of 2 arrays connected into the MPPT. One array is 198 cells, one array is 59 cells. And it does use bypass diodes, which is between panels to optimize performance. Our planned upgrade is to increase our size to 6 meters squared, which is significantly larger. Well, there'll still be 2 arrays. One array will be 220 cells, and one will be 108 cells. Currently, we're very fortunate to have all the panels we need for this upgrade. Our next semester goals are to finalize the attachment methods of the panels for the car. We have many ideas planned, but we want to make sure we can implement some. Next, we want to do is install the new array, and by new array, I mean the expansion of the array up to the extra 2 meters squared, if you will. And lastly, we want to test the MPPT to make sure it is working properly with these new panel upgrade and recode as necessary. Thank you.
So the hardware integration sub-team is responsible primarily for the design of the low voltage electrical system that Will overviewed. This includes, lights, horns, controlling the motor, other things like that. And we mostly design the PCBs that power this system, as well as the wiring and external hardware that make it all possible. So our current projects for this year are to, 1, protect our current electrical system because it is a working system, although it has flaws. It will provide a good backup in case something went wrong with the new system. And we're also attempting to address some of these flaws with the current system and revise it for a new set of boards for the version 3 of the low voltage system. So, protecting our old system is mainly by creating enclosures to house them. We are experimenting with a few different lid attachments and ways to secure the 2 parts of the enclosure together. And all the enclosures will be 3D printed and they're custom designed for the specific PCB they're housing. This will hopefully protect the boards from various debris and improve their security and mounting efficiency on the car. More importantly, we are working to create an improved set of PCBs for our new electrical system. The main feature of this is the modular STM. Try to think something like a smaller, more specific, specialized version of like a Nucleo board, where we can be able to program our STMs and power them, debug them, all on their own separate board, and then we can slot that board into any board that we make with a custom footprint. And so this will provide easier switching out of microcontrollers as well as additional flexibility with our system, and it will allow us to standardize our board designs, make them easier to include microcontrollers on these boards, and then we can create our main goal of a distributed electrical system. So this is our schematic right now, first draft of the schematic for the modular STM. As you can see, it has the debugger for programming and has the actual STM with the breakout pins that will slot onto the other board. And we also have schematics for CAN translation and powering the STM itself. You can see that here, there's our power conversion circuits, basically just stepping down 12 volts to a stable 5 volt source and then to a stable 3.3 volt source. Those are the voltages that the STM needs for its logic. And this is our custom symbol. This is what will be on any other board that we make, and that provides the interface that we will use to access the modular STM from any of our other boards. And this is all with the goal of creating a more distributed logic system for our PCBs. One of the main problems we encountered right before the race was our STM that controls basically all of the car's logic fried, and nothing on the car worked. And without the the happenstance of we had these jumper pins connected to test all the different STM pins, and we were able to jump a Nucleo board's outputs to that and provide the same functionality. But in the future, we may not have this random occurrence that we weren't planning for. And so we would like to have a better system of STM boards that can be swapped out and replaced very easily. And it will also give us the opportunity to go from one microcontroller to 4 on separate boards, which will allow us to distribute our logic based on location. This will also cut down on connections, especially analog connections. Everything can be sent through CAN to different microcontrollers. And this will also allow the boards to monitor more signals, provide more safety checks, and if needed, if one microcontroller is to break down, we can reprogram some other ones to take on some of that functionality. And hopefully this will also reduce the number of PCBs that we need to use. As you can see in this image, this is one of our boards that we've finalized the first draft of for the distributed system. It has our new symbol, and basically, whereas this board previously distributed power to all the lights, it now takes signals from CAN and determines which lights to turn on and uses the STM board, the modular STM board, to do that and power the lights all on the same board.
Hi everybody, I'm Mark, I'm the mechanical director.
I'm Liam, the aerobody and composites lead.
I'm Reed, I'm the chassis lead.
I'm Cole, I'm brake and steering.
I'm Landon, I'm part of the aerobody team.
I'm Oren, I'm part of the aerobody team.
I'm Rex, I'm the suspension lead.
So a brief overview of the mechanical team itself. We're in charge of making the mechanical components of the car. First off is the aero body, which kind of is the outer shell of the car. It has the solar panels on it, and it's made out of carbon fiber. And then attached to the aero body is the chassis, which is the main component of the car, where it has a double wishbone front and back suspension, and then uses a rack and pinion for steering. And then we also use hydraulic brakes. As you may know, this past summer we went to FSG 2025 and we had a lot of race setbacks where we weren't able to pass scrutineering. And one of the biggest reasons was a failed dynamics testing. And that was because of the inability to pass the brakes and steering stability test and then the slalom test. So the slalom test is where you go in between cones when you're turning constantly. And then the brakes test is where you go in a straight line and then you brake. And the problem is that we had a lot of steering instabilities. And this was mainly due to weight distribution, where a lot of our weight was in the back. So we were back heavy, and because of that, the front acts as a pin, and you kind of just wobble a lot. So you can't really steer in a straight line. And then that, coupled with the play in the steering, where there's a lot of looseness in the steering, led to a lot of instabilities that the scrutineers didn't like. And you can see in this video, you can see us wobbling a lot in the straight line. And then as we're braking, you can see we start to turn, which is not what we want. And that's kind of where the scrutineers were like, that's no go. So our main goal this semester has been to try and fix that problem. And one of the biggest fixes is the weight distribution itself. And our major design for that is the trailing arm suspension. So essentially, like I said previously, we use a double wishbone for front and back suspension. And as you can see here, that leads to the center of mass being right here, which is the 70% in the back and 30% in the front weight distribution. And to prevent that from happening again next year, we're going to move that pin or the suspension back a little bit, leading to a 55% weight in the back and then 45% in the front. And then to fix the play in the steering system, we will be redesigning that and to add more rigidity to the steering system. And then a lot of the other sub teams will have a different like design changes for to meet a lot of other goals for the scrutineering, and I'll let them talk about that.
Hi, so I'm Liam, the Aerobody and Composites lead. I'm with two of my very important members here. The Aerobody and Composite team works with composites to create the outer shell of the car, as well as any of the systems that work with the shell and connect to other systems of the car. So an important project we've been working on this semester is top shell hinging. The purpose of this design is to allow quick access to the interior of the car, and then also to angle our solar panels to quickly recharge the car. This also helps secure the top shell together for our latching design, which will be shown later. And then we designed this to easily lift up our about 90-pound top shell.
So I'm Landon. I'm the one who's been kind of catting this whole design for the hinging. The main points that I kind of had to go for when designing this was, first of all, as you can see in this animation, we kind of wanted to do a hinging set in the front, in the back, and in the front with kind of two hinging rods on each. This would allow for better control and more stability when opening and closing the top, so that you can kind of lock the motion so that it's not kind of wobbling as you open it. To do this, I had to align the axes of the hinging so that they wouldn't lock each other or get in each other's way when trying to open it. But the problem with this is, since our car is sloped, the hinging point in the back is much higher than the hinging point in the front. To combat this, we actually ended up having to take our bulkheads, which are usually 90 degrees to the car, and tilt them about 6 degrees forward so that the axes will actually line up now. Additionally, we chose to make the hinging rods curved, whereas they were originally straight. This curvature allows for a rotational opening as opposed to a more linear one that the straight ones gave. This allows for, one, just a better angle to be achieved with the rotational opening, and two, our car has like a 2-inch extrusion all around the top of the bottom shell. This is modeled by this little lip right there, and so that curvature allows us to kind of wrap around that instead of running straight into it with the straight rod. And then finally, I had to figure out how to attach our telescoping rods, which would be used to prop up the shell when open. Originally, we had planned to kind of lock these in place, but we figured that that would not be optimal, so we are choosing to go with more of how a car hood works, where when you open that, there's a rod that you pull up and prop it open with. That's how we're going to use those. We'll have a connection point kind of near the top, so when you open it, you just pull that out, connect it to where it is, and it can hold it open. Our maximum angle of the top shell that we ended up able to achieve was about 45 degrees, which allows us to point our solar panels directly at the sun and collect as much energy as possible. How we are planning to attach these rods to the bulkheads into the connection point is through this 3D modeled connection, which Oren had been working on.
Yeah, so I'll talk a little bit about these connecting points. So these are designed and primarily made to be 3D printed. We'll then glass them into the telescoping rods with some carbon fiber or fiberglass, and then they'll just sit on a bearing, and they'll be able to rotate and move those telescoping rods.
And then we also have this aluminum hard point, which we figured would be one of the weakest connection points for the system. We did some calculations with the compressive strength of the honeycomb and a factor of safety of 3 to determine what bolts to use and the size of these aluminum hard points. We also have this new bulkhead that will allow for our hinging system to work, and then also allow us to remove the chassis from the rest of the car. So we have about 3 inches of clearance from the ground from which to pull our new trailing arm suspension out of the car. And then we also have a slot cut in the top of that bulkhead to allow for the movement of our telescoping rods.
Yeah, so we're talking about this bulkhead being 6 degrees off center, but how do we actually get it to be that 6 degrees angle? And so I created this jig that will sit at the bottom of the car, and we'll be able to slot the bulkhead right into it. So we'll do that for the back bulkhead. Then we'll, after we drill that hole to attach the hinging arms, we'll then take the bulkhead out. We'll then shine a laser through to the front bulkhead, find that exact point, take that bulkhead out, drill the next hole. And this will guarantee that our points are directly coplanar and will allow the hinging to work perfectly.
And then finally, we have our latching design. This is an important part of the regulations that connects the top shell to the bottom shell. And Solar Car has struggled with this in previous years. Our designs have met the regulations but have been slow and clunky to work with. So this year we're hoping that our design will be much cleaner to work with. And that will work in tandem with the hinging system to ensure that our latches are always aligned with each other. So we're going to be using a hood pin at the front of the car shown at that red dot. This will protrude off of a rib on the front hood and then go through the top shell and just be secured by a pin. And then we're also going to use a rotary latch, which will be pointed downwards from the top shell and then connect to a strike bolt, which will be mounted on the bottom shell. And then that can be accessed and opened with a small slot in the side of the car and pin.
Hi guys, I'm Rena. I'm the chassis lead for this year. So basically, we focus on maintaining the primary structure of the car, driver operations, and integrating other sub-team projects into the chassis. Okay, so our main semester goals for this semester were to create and redesign a new ballast box and to create and design a new suspension chassis extension. So the ballast box is a box kept in the back of the car near the driver that holds a bag of lead shots, and this ensures that the driver weight distribution across all 4 drivers is relatively the same during the race. So this year we decided to redesign a ballast box using honeycomb and fiberglass composite layups to reduce the overall weight of the ballast box. In the CAD model, as you can see here, it's usually kept in the back of the driver's seat, right near the driver's hips. But we're hoping to change the position of this box to increase accessibility during the race with the addition of top shell hinging. Our second project was the chassis extension. We had 2 designs created by 2 of our members, Jackie and Elijah. One design had 3 bars and one had 4 bars that would be attached to the parallel to the back end of the chassis to allow the trailing arm suspension to be integrated into the chassis without reducing the overall back wheel width of the car. However, we decided that by attaching the trailing arm suspension directly to the back of the chassis, the wheel width would stay the same relatively to the front of the car, so we decided against using this design. However, overall, this was good CAD practice for our members and helped increase practice of fundamental skills. Looking on to next semester, we're hoping to collaborate with hardware integration to create wire boards that fit directly into the chassis to create seamless electrical integration and to reevaluate and redesign our driver's seat to increase driver visibility and comfort of the driver during the actual race.
Hi, I'm Cole. I'm the brakes and steering lead. So we're in charge of designing basically all the driver's inputs into the car. So the steering wheel, the braking system, we have multiple braking systems, and the connections to the chassis and suspension. So we've been basically working to redesign and remanufacture every single part of the system. We had a lot of issues at the race last year, so we just kind of wanted to just start over and do a better job this time. So I'll go through the different projects, but it also includes more advanced braking sensors and better reliability and ease of repair. We had a lot of trouble at the race actually being able to take things apart and access them. In fact, we spent over an hour just trying to remove a single bolt before we realized it was stripped. We just cut it. So we want to not have that happen in the future. And then finally, we've been working on teaching members how to use SolidWorks, FEA, hand tools, and general mechanical engineering design principles. So one of the first projects we're working on is with our brake pedal. Most cars you'll see have a brake pedal with a swing mount where your foot goes down to press it. And previously we had a floor mount, and that made it actually very difficult for the driver to brake. So we're basically just flipping it upside down. It'll also make it a lot easier for us to access the bolts that are on there. We're also integrating magnetic position sensors into the brake pedal to give us data to know how far it's pressed for activating the brake lights. We're redesigning our brake lines. You can see a schematic here. So we're going to use hard lines, which are basically just like copper or nickel-plated pipe, instead of soft, flexible lines, which just became a bit of a tangled mess, especially at the front where they got in the way of our steering. So this will be just a much cleaner brake line layout. It'll also allow us much more flexibility on where we add our sensors. So here we'd have a pressure sensor, a hydraulic pressure sensor that provides redundancy for our position sensor in the brake pedal, and it also will provide us some early warning if we start having brake line leaks. And then we're also going to have a new mount for our accelerator plate, which is on the left there. And this mount is just easier to attach, and it also doesn't cover up our tie rods, which are how the steering wheel pushes the wheels back and forth, which our previous design had, which basically made it so if you wanted to access the tie rods, you had to take apart both the pedals first, which is not great. Moving on to the steering. So our most ambitious project this year is designing a brand new steering shaft. In previous years, we've had issues with both egress as well as drivers of different heights having trouble reaching the wheel. And so this is an adjustable shaft. You can see it's hexagonal. There's an outer and inner shaft that can slide back and forth and rotate the U-joint there. And you'll see those holes on the side. Those are for a pin connector, spring-loaded pin. So basically how this works is right where the cursor is a paddle. The driver would be able to pull that out. It would pull a cable which would run across these two pulleys internal in the shaft, come out, and then pull on a plunger. So you pull it out, and you're able to just push the shaft back and forth and lock it in place with a pin. Additionally, we have a new steering shaft support, which I'll show on the next slide. We have a new steering arm. So you can see this little bit here is a steering arm. Our previous one was just a piece of sheet metal, which had some flex, as Mark mentioned initially, which creates slop in the steering system. So this design is much more rigid. It's also attached to the side of the upright because we noticed that there was actually very little space on our upright itself. So you can see that axle there. It looks like there's plenty of clearance. In reality, that axle really goes to about here, which is not great. You want to have clearance outside of the nut. So we're both shaving down our upright to add more space and mounting on the side just to clear up more space on that axle and provide more rigidity for the steering arm. And then we're also going to work on a better manufacturing plan for tighter tolerances. Part of the reason why we had so much slop in the steering shaft is because we were not really cognizant of how we were going to do our manufacturing design, how are we going to spec parts, tolerances, fits, etc. So we're going to be very conscious to make a clear effort to do a better job with that. And just to highlight a few other things I mentioned on that slide, this is removable steering shaft support up on the top right. It's triangular, so it provides much better resistance against bending. It would have an internal bushing there to support the steering shaft, and it would also be removable, so you'd have screws on either side. You can take it apart and basically just release the steering shaft so we can access all those parts easier at the race. On the left here is a CAD of our steering wheel. Hardware integration already talked about the screen there, but we work on the mechanical part of the wheel. And this wheel is really awesome. It was designed last year. We're going to fix those grips, which are starting to slip off. But mainly we're going to add this paddle you see here on the left, which allows you to actuate the cable system to control the steering shaft in and out. And then lastly, on the bottom right here, we have our steering stops. These are really important for preventing unwanted travel. So if the tire turns too much, the tire will actually rub against the chassis, which obviously is not good. So this steering stop nub is just welded onto the lower wishbone, and then it contacts our brake plate, which we would just extend slightly down to prevent unwanted contact. Lastly, we're redesigning our handbrake. So last year our handbrake worked, and the handbrake, by the way, if you don't know, is just our parking brake. So when the car stopped, you just lock it in place, just like any other car. The problem was our handbrake only had one position it could be locked to. And sometimes that meant that it was either too firm or too soft if the pressure in the braking system changed, which it often does. So this year we have a new ratchet and prowl style mechanism. This little prowl here contacts this plate and it ratchets. It has a spring which holds it against this base plate, and as it ratchets, it locks in place. And then to release it, you pull this lever here on the right, which just lifts it up and allows you to move it back in position. So this will just make it really easy for us to park our car. And then to attach it, we have these welded brackets you see on the left, and it'll mount right on the side of the chassis, as you can see there, instead of mounting to the floor, which is really hard to remove.
Yeah, hi guys. Again, I'm Rex. I'm the suspension lead. What suspension does? It's just like okay. We get this great spinning 3D model. Yeah, suspension. We're just the system that attaches the wheels to the chassis. Okay, so for this entire presentation, you guys have been hearing about this mysterious, nebulous trailing arm suspension. Hope I can prove to you guys that it's a simple and elegant solution to the problems that we've been facing. So, what is a trailing arm suspension? Very simple. It's a suspension arm coming directly off of the rear of the chassis, as opposed to most other
suspensions designs that are coming off the side of the chassis. So why are we doing this? As mentioned by Mark before, our current center of mass looks a lot like that picture on the left, where we have 30% of the weight in the front, 70% of the weight in the rear, which causes a lot of steering instability and other issues. So with the addition of this trailing arm suspension, the new center of mass would in fact be slightly more towards the back because we're moving the wheels and the suspension backwards, but the distribution between the two wheels will be a lot more even, with 45 in the front, 55 in the rear. So that's the main reason why we're doing it. Another big reason why we've decided to move to this design is because it's much simpler to design, manufacture, and work on compared to other suspension types, such as the double wishbone that we've been working with. So yeah, most suspension, double wishbone particularly, there's a lot of angles you have to worry about, camber, toe angle, caster, and small adjustments to these angles can seriously impact the stability and drivability of the car. Trailing arm, I'll go into more of how this works in the next slide, but it pivots only along one axis. So all these angles you basically don't have to worry about. So it's a whole lot simpler. And yeah, for double wishbone, when not only designing but also working on it, if you take it off, for example, and you're adjusting things, you put it back on. If you're not very particular about how you put it back on, then those angles end up becoming different. But with a trailing arm, it's very simple it's just 3 bolts that you put on, and none of those angles ever get changed. So it's going to be a lot easier to work on. Will it fix our problems? Maybe not entirely. We still have double wishbone in the front that we have other plans to work on, but it is very definitely a step in the right direction with improving our center of mass and simplicity. Okay, so closer look at this thing. As you can see, this is a side view. It is just pivoting along this axis. The spring is providing the force, keeping the wheel down and the car up. The way it all comes together, this entire tube is one single welded piece of multiple pieces of aluminum. We have a bracket coming at the end where the wheel attaches, where the brake calipers attach, and we have a shock absorber right here, the same thing. And these 3 sets of weld tabs, 2 heim joints and 1 other connection up here, is where the entire thing pivots. Okay, so let's go through some major design choices that informed the way this thing looks. The most prominent looking feature is this sideways extension. During our design reviews while we were developing this, a lot of parties had mentioned the fact that if we did not have any kind of sideways extension like this, the wheels would be a lot closer together, so our wheelbase would be less than it had been previously. And this can cause a lot of problems. Notably, it can increase the possibility of rolling over. It just decreases your stability in that sense. So we had been racking our brains of thinking a way to fix this. As Chassis mentioned, one possibility that we considered was to have a sideways chassis extension. So you can imagine this entire thing being mounted slightly further off the side of the car with the chassis extension. We decided eventually that this, having the sideways extension on the trailing arm itself, was a simpler and more elegant solution. So that's why we've gone with this. Additionally, you can see the location of the spring. It does look a little suspiciously close to the chassis, like it won't provide enough force. But we did, in contrast to previous years, with this design, we paid a lot of attention to what the spring constant of that spring is and all the equations involved to determine exactly where it should go to provide the optimal force on the wheel. And so the tubing size, the size of those heim joints, the size of the nuts and things that we were putting in, that was all decided through extensive FEA analysis. We eventually decided on 1.25 inch outer diameter tubing, which is relatively beefy, but it's going to make sure that this thing does not snap on us, which would be quite problematic. Okay, so the materials involved in manufacturing. I mentioned this, we're going to use roughly 2.5 meters of 1.25 inch outer diameter steel tubing. We're we're going to be using shocks and forgot to mention the shocks that we're using. They're from a previous car, Rivanna 2, that we found to be ideal for us. We're going to be using some fasteners from previous cars that are easy to reuse. Everything else is just going to be steel tubing, a steel plate at the end. All that steel is so that we can weld things easily because, as you can see, all this drawn in red is welded connections. So this entire thing is just going to be one single component, which, as I mentioned before, is much easier to work with. In order to get all these welded connections very precise, to bring this CAD into the real world, we're going to be researching and implementing a 3D printed jig, which basically it's just a set of holders that you can place all these tubes that you've cut. You can place them in very precise locations, and then you can weld it all together from there so that we're bringing what's in the CAD into the real world. That is all.
Yeah, so just for a little bit for next semester, our next steps. So currently, as you can tell, our members and leads have taken a lot of time in deciding their designs, and they've turned out very great. So next semester, we'll work on manufacturing. So over winter break, we're looking to basically finalize a manufacturing plan and get all the materials necessary. And then by mid-February, we hope to basically build all these designs outside of the chassis. And then early March, we'll have everything implemented and ready to go.
All right. Thank you, everyone from the team. Looking forward to next semester, as Mark already kind of hinted at. First thing we're going to do is recruit and onboard new members. And we have been talking about it as a team, and this is the first time we're going to be having no application in order for new members to join our team. And this is just going to increase the outreach that we have. We hope to give this experience that's been so wonderful for us to even more people. So once we get those new members, we'll onboard them and hopefully bolster the strength of our team. Then we're going to do even more concessions at the basketball games to raise even more money, continue the strong momentum with the social events that we all love. Then, like Mark said, manufacture our final designs, whether that be the electrical, the battery, any of our boards, our suspension, or any brakes and steering projects. And then, of course, integrate that all onto the final car so that we can test it, which the main thing is that we're going to do the dynamics testing, which is where we failed this previous summer, specifically in this figure 8 and especially the slalom test where you just go kind of snake in between cones. And that's going to be earlier in the spring semester, March 22nd, so that hopefully, we have time to make sure that everything's working and that once we get to the race and we have to do these tests for real, that we get them done, one and done, hopefully. And then finally, we have to finalize all our documentation for the race, finish our design reports, get all the logistics ready, hotel, food, all that sort of stuff, so that we're ready to succeed and hopefully reach that goal of qualifying for ASC.
Yeah, so for this past hour, you've seen all the stuff that we've been working on, all the designs, and all of the good things that we were working on. And I hope that you can continue following us more in the future. But that's basically our presentation. Before we head off into our light refreshments, I want to first thank our advisors, all the members on our team, Professor Barnes and Professor Garner, all of the parties that we have asked for design reviews, Sebring, Peter Dow, Virginia Motorsports teams, and a bunch of our other alumni. So thank you so much, and thank you so much for coming and presenting. And please ask us if you have any questions, and have some light refreshments. Thank you.